Hi everyone, William here, and today's question is the universe a hologram? Now, my position on this might actually surprise you a bit, because my answer is, I don't know, but it could be. So we need to touch on a few ideas in physics, high level of course. We need to start with quantum entanglement. If you haven't heard of this, essentially it's when you have two separate particles that are of the same type, but separate particles, quarks or electrons, something like that, that are bound in a particular way. When the particles are right beside each other, you can see that they have different spins, opposite spins. But here's the crazy part. If the spin on one particle is changed, the spin on the other one will change at the exact same time. And I mean exact, it's instantaneous. No matter what the distance is between the particles, it's instantaneous. No delay at all. And this has been replicated over and over again. Now, this poses a large problem for one of our best known and established theories out there, that of relativity, which you've probably heard of. We can talk about that sometime, if anybody's interested. But now, you just need to know that a major implication that comes out of relativity is that nothing can move faster than the universal constant, also known as the speed of light. But obviously, in the example we just talked about, the particles are reacting instantaneously, and therefore the signal between them must be going faster than the speed of light. Or is it? Let's go back to the particles. They have opposite spins, right? Let's think of an analogy real quick. And that is that you're looking at a closed circuit TV screens, two of them. And they show two different goats, what appear to be two different goats. One shows a goat from head on, and one shows a goat from the side. Now, all of a sudden, the two goats move at the same time, but opposite to each other. So what would be your immediate conclusion? Probably that you're looking at the same goat, but from two different camera angles. That's reasonable. Could this be what's happening to our entangled particles? Are they actually the same particle, and we're just being duped by an illusion? I haven't mentioned holograms yet. I'll get to that, but I need to talk about black holes and entropy first, because it's related. Now, I'm not going to give a whole history on black hole research, just the part that's relevant to this discussion, which is black hole, entropy, and information theory specifically. Now, entropy, I'm sure you're familiar with the word, in everyday parlance means disorder or chaos. But in thermodynamics, it has a different meaning. It means, well, it's not different, but it has a specific meaning, which is it's a measure of the quality of the energy, with potential energy being on one side, like fuel. It is less entropic than something on the other side, like heat, which is less useful and therefore more entropic. Now, there's an important law in thermodynamics. It's called the second law of thermodynamics. And it says, in a closed system, entropy must increase over time. So in the long run, all energy gets converted into heat, which is bad for us ultimately, because this means that the universe will ultimately cease to function, and we will have what's called the heat death of the universe. But that's a long time in the future, so don't worry about it. Don't lose any sleep over it. Now, entropy has a more specific but ultimately identical meaning in physics, and it is the count of the number of ways that you can possibly fit something, we're usually talking about energy in here, but it doesn't have to be, fit something into something else, the number of combinations or permutations. This is known as information in physics, as in information theory, which you may have heard of. Now, there's a textbook example that I'll give, which is that if you poured sand into a bucket, there'll be a whole bunch of possible ways in which those grains of sand could be configured in that bucket. If you counted up all those possible ways, the number of possibilities, that's the maximum amount of information that the space can hold. So it's clear that the amount of information that a space can hold is directly related to its volume. Or so we thought. So along come the black hole scientists, and they're disputing some details related to entropy. And that is specifically whether or not black holes violate that second law of thermodynamics we just talked about. Now, Stephen Hawking, who I'm sure you've heard of, He's most famous for having figured out a solution. And that is that black holes would have to radiate energy completely unrelated to the energy and mass that it collected in order to not violate the second law. When I say unrelated, I mean in type, not in quantity, because it would be related in quantity. And we believe this to be true through observation since then, and we now refer to that radiation as Hawking radiation. We named it after him. But included in all of this work was an amazing discovery. And that is that the total entropy of a black hole is not proportional to the volume. And the volume I'm talking about is the volume of the event horizon. The event horizon is that volume around a black hole which contains all of the information concerning all the mass and energy that the black hole is attracted. But instead of the volume, the entropy is actually proportional to the event horizon surface area. So what does that mean? That means that all of the black hole's information is contained on the two-dimensional surface of the event horizon. And this surface is akin to the two-dimensional inside surface of a sphere. And all the space inside this sphere, meaning the entire volume, is described on that surface. So let me get to holograms for a second here. And what is a hologram? A hologram is a photograph, basically, of a 3D object taken by different lasers. And a laser, of course, is just focused light. The interference pattern created by those lasers is then projected on a 2D surface. When another laser is pointed to that 2D surface, that stored information is then revealed into a third dimension. A hologram has another key difference from a normal 2D photograph. And that is that if you were to take a normal photograph and cut it in half and throw one half away, you would have just thrown away half of the photograph's information. But if you do this to a hologram, you still have all the information. You still have the full 3D image. That's because each individual pixel of the hologram holds the entire hologram's information, all of it. Now, this appears to be exactly what the surface of the black hole's event horizon is doing. It's amazing. So let's go back to the beginning of this and recall the problem that we had with the particle entanglement. The particles appear to be reacting instantaneously. When one is affected, the other one's affected. But how can they do this when there's a distance between them? The answer? There is no distance between them. If the particles are in fact one particle on a 2D surface, a two-dimensional surface that is projected onto a third dimension, then there would just be an illusion of this distance between them. The real distances would be on the two-dimensional surface only. And here's the crazy thing. The math involved here works out, and our observations so far are consistent with this hypothesis. In fact, it provides a solution to the problem of the incompatibilities of quantum gravity, a completely different subject. But just know that it does that. We could very well live in a two-dimensional universe and basically have tricked ourselves into thinking there's a third dimension. And to anybody who's read about string theory, this does not preclude the existence of the 10 or 27 spatial dimensions that are required by string theory. They would just be very small and inconsequential in this 2D universe, just like they would be in the normal, what we think is the normal 3D real universe, so to speak. Now, all this may seem really unlikely, but think about how we perceive things in the universe in general. We experience space and time from a very narrow viewpoint, one that has low energies, low velocities, low masses by comparison to other places in the universe. So how could natural selection produce traits that would allow us to perceive these other frames of reference if they're not normally present here? Even here on Earth with limited variability in the energy, mass, and velocity, we still have a huge diversity of sensory detection spans in the animal residents of the planet. For example, animals see different parts of the electromagnetic spectrum. They have different hearing frequencies, the ranges, they're different. And some animals, it at least seems that they can detect magnetic fields. So is the universe a hologram? I don't know, but it seems like it could be. This, of course, does not mean that the holographic universe will be a viable theory and ever. It just means that we'll be trying hard to falsify it, the hypothesis. So far, there does not appear to be an agreed upon experiment to actually figure this out, but it's being worked on, I assure you, right now. And I do need to point out that even if the universe is a hologram of the type that I just described, that doesn't mean that we're living in a matrix-like simulation created by aliens or something like that. But if it were confirmed, it would fundamentally change and improve our understanding of the nature of the universe. Anyway, I hope you found that interesting. Please like and subscribe. Let me know what you think about it. Be kind, be safe, and I'll catch you later.